Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a Hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green.
When we say light, we actually mean visible light, which is a tiny part of the electromagnetic spectrum, energy in form of electromagnetic radiation. Electromagnetic radiation consists of an enormous range of wavelengths and frequencies. Gamma rays have the smallest wavelengths because they're the highest energy photons, but most gamma rays are just under 10 picometers, which is still way smaller than a hydrogen atom. For reference, a hydrogen atom compared to a cent is about as big as a cent compared to the moon. Visible light is in the middle of the spectrum, in the range of about 400 nanometers to 700 nanometers, about the size of bacteria. On the other end of the spectrum, radio waves can be up to 100 kilometers in diameter, while the biggest wavelengths we know exist can span from 10,000 kilometers to a baffling 100,000 kilometers, way larger than Earth. From a physics standpoint, all these different waves are the same. They all have the wave-particle duality and travel at c, the speed of light, just at different frequencies. So what makes visible light special then? Well, absolutely nothing. We just happen to have evolved eyes that are good at registering exactly this part of the electromagnetic spectrum. This is not a complete coincidence, though. Visible light is the only set of electromagnetic radiation that propagates well in water, which happens to be where most eyes first evolved millions of years ago. That was a smart move because light not only interacts with matter, it's also altered by it and can be used to gather information about the world around us with almost no delay, which is arguably really helpful for survival.
What if you could only see one color? Imagine, for instance, that you could only see things that were red, and that everything else was completely invisible to you. As it turns out, that's how you live your life all the time, because your eyes can only see a minuscule part of the full spectrum of light. Different kinds of light are all around you every day, but are invisible to the human eye. From the radio waves that carry your favorite songs, to the X-rays doctors use to see inside of you, to the microwaves that heat up your food. In order to understand how these can all be light, we'll need to know a thing or two about what light is. Light is electromagnetic radiation that acts like both a wave and a particle. Light waves are kind of like waves on the ocean. There are big waves and small waves, waves that crash on the shore one right after the other, and waves that only roll in every so often. The size of a wave is called its wavelength, and how often it comes by is called its frequency. Imagine being a boat in that ocean, bobbing up and down as the waves go by. If the waves that day have long wavelengths, they'll make you bob only so often, or at a low frequency. If the waves instead have short wavelengths, they'll be close together and you'll bob up and down much more often, at a high frequency. Different kinds of light are all waves, they just have different wavelengths and frequencies. If you know the wavelength or frequency of a wave of light, you can also figure out its energy. Long wavelengths have low energies, while short wavelengths have high energies. It's easy to remember if you think about being in that boat. If you were out sailing on a day with short, choppy waves, you'd probably be pretty high energy yourself, running around to keep things from falling over. But on a long wavelength sea, you'd be rolling along, relaxed, low energy. The energy of light tells us how it will interact with matter, for example, the cells of our eyes. When we see, it's because the energy of light stimulates a receptor in our eye called the retina. Our retina are only sensitive to light with a very small range in energy, and so we call that range of light visible light. Inside our retina are special receptors called rods and cones. The rods measure brightness, so we know how much light there is. The cones are in charge of what color of light we see, because different cones are sensitive to different energies of light. Some cones are more excited by light that is long wavelength and low energy, and other cones are more excited by short wavelength, high energy light. When light hits our eye, the relative amount of energy each cone measures signals our brain to perceive colors. The rainbow we perceive is actually visible light in order of its energy. At one side of the rainbow is low energy light we see as red, and at the other side is high energy light we see as blue. If light shines on us that has an energy our retina can't measure, we won't be able to see it. Light that is too short wavelength or high energy gets absorbed by the eye's surface before it can even get to the retina, and light that is too long wavelength doesn't have enough energy to stimulate our retina at all. The only thing that makes one kind of light different from another is its wavelength. Radio waves have long wavelengths, while X-rays have short wavelengths, and visible light, the kind you can actually see, is somewhere in between.
It's time to learn about ultraviolet light. It might save your life. That's because ultraviolet light is more energetic than regular light. We sometimes call it ionizing radiation because it has the power to ionize the electrons in molecules, like DNA, and cause damage. UV light is invisible to us, but its energy can make other objects glow, like this pair of socks. They absorb the UV light and release that energy as visible light. It's actually the detergent residue that glows and makes them look really clean, whiter than white. It doesn't always take UV to make things glow. I can get these fluorescent liquids to glow just by using a blue light. But I can't get the green or yellow by using the red light. There's something that blue and violet lights have that the other colors don't. They are more energetic, higher in frequency. Their high frequency light is absorbed and re-emitted as lower energy light. These plastic beads are sensitive to ultraviolet light. Even in sunlight, they will change color. But I get a different effect when the sunlight passes through a pane of window glass. That gives us a clue that there are multiple colors of ultraviolet light. Unlike visible light, ultraviolet light is sometimes blocked by glass. These fluorescent rocks glow in multiple colors when exposed to UV, but this clear glass pane prevents much of this. Some of the UV still gets through though, but not all. The three colors of UV are named near, mid, and far, or UVA, UVB, and UVC. The sun emits all three. UVC is the most energetic, and it's easily blocked by the atmosphere and glass. It is sometimes produced artificially by people to kill bacteria on tabletops, keyboards, meat, and treated sewage. UVB is partially absorbed by our atmosphere, especially the ozone layer, and it causes sunburns. UVB is blocked by glass, so you're less likely to get a sunburn through glass. This is quartz. It's made of the same material as glass, but it's extra pure and cooled slowly. And unlike regular glass, quartz is transparent to UV light. I have here some man-made quartz glass on this UVC lamp. Like I said, it has to be very pure. It's the impurities in glass that do most of the absorbing. Here's a piece of willemite illuminated with UVB. A common glass microscope slide blocks the UV light, but a quartz glass slide has no effect. Quartz glass is transparent to ultraviolet light. Then there is UVA. This is the ultraviolet and black light, and this is the type that is not blocked by glass. Unlike UVB, UVA penetrates deep into the skin and causes damage beneath the surface. Along with UVB, UVA is the type that causes the most skin cancer. Therefore, we cannot rely on glass alone to protect us from UV light. We need sunblock. Most good sunblocks and sunglasses will advertise that they block UVA and UVB, broad spectrum. They don't even bother to mention UVC because there is so little of it that reaches Earth's surface. Electrified mercury vapor gives off a lot of ultraviolet light, and for that reason, we often use it in fluorescent lamps. The UV light is absorbed by the fluorescent paint on the inside of the glass. That paint glows in a convincing white. But isn't spending that much time under ultraviolet light dangerous? Well, once again, the glass protects us from the more energetic UV. This is the Mercury spectrum. I'm projecting it onto a piece of styrofoam. The ultraviolet light is normally invisible, but this piece of paper fluoresces to show where the ultraviolet lines are. This is the experiment that first convinced me that ultraviolet light was real. Inspired by William Herschel's discovery of infrared light in 1800, Johann Ritter performed this new experiment in 1801. Ritter again split the sunlight with a prism into the normal rainbow. He arranged for the light to land on silver chloride salt, which turns brown when exposed to light. 20 years later, this chemical would be used to make the first photographs. Anyways, as expected, there was an invisible light beyond the violet side of the spectrum. It's a well-known fact that insects can see ultraviolet light, and most people think this is so they can see flowers better. But that's incorrect. The insect predates the flower by hundreds of millions of years. It's the flower that is adapted to the eyes of the insect. Insect eyes see UV because the shorter wavelengths offer advantages to the eyes of small creatures. First of all, when your eye is smaller, you want it to be sensitive to more energetic light, because then you will need less of it to see. And secondly, the shorter wavelengths reduce the diffraction effects, which allows for insects to have smaller eyes, and hence more compound eyes, and thus better insect vision. Many flowers have distinctive markings that are only visible in the ultraviolet. like little bullseyes, evolved to attract the pollinators. What do your students need to know about infrared light? Well, it's an electromagnetic wave, just like regular light, except that the wavelength is longer. And it's invisible to the human eye, but not to snakes. When we say that snakes see infrared light, we only mean that they are sensitive to it. The pits on the face cannot actually focus the light, and so that it's mostly just used for triangulation. The ability to sense the heat of an animal seems to have evolved independently in pythons and pit vipers, including the rattlesnake. You can experience a similar sensation to a snake's heat vision by gently closing your eyes and pointing a flashlight at your face. The light is bright enough for you to triangulate its position by turning your head, and when both eyes see the same thing, you'll know that the light is right in front of you. That's what it's like for the snake. They do not actually see their prey, they only sense it. This glass prism can separate the sun's light by its color, or wavelength, and this is how infrared light was first discovered. Astronomer William Herschel projected the solar spectrum onto black painted thermometers to find out which color was the warmest. He was using mercury thermometers. You can imagine his surprise when the warmest color turned out to be an invisible color that he didn't even know about, beyond the red side of the spectrum. Now, he recognized immediately that this was a new form of invisible light, which he called calorific rays. You can repeat Herschel's experiment exactly as he did it, but you might prefer to use one of these, a temperature-sensitive liquid crystal sheet. When it gets warm, it changes color. So, which color is the warmest? Once again, it's the invisible calorific rays, which these days we now call infrared, meaning lower than red. Point your TV remote control at a camera and you can clearly see it flickering as you press the button. That's infrared light. The camera misreads it as a purple. Near infrared is used in TV remote controls and military lasers. Intermediate infrared guides heat-seeking missiles because really hot machines glow brightest in this color. And then there's far infrared, which has the longest wavelengths. Far infrared is the type of light seen by thermographic cameras, and it's given off by objects just warmer than room temperature, like you. Many substances that are transparent to visible light are opaque in the infrared, and vice versa. For example, this glass jar blocks the far infrared light so you don't know what's behind it. On the other hand, this black plastic bag is perfectly transparent in the infrared so you can see right through. This is ice in warm water. Now, hot water. Aw, look at this adorable mouse. It wants to hide in this bag. But what it doesn't know is that I have a thermographic camera. Far infrared light is often used to find hidden objects that have a heat signature. It even works in the dark. Here I am comparing the light from the TV remote control to a candle. When we look through the diffraction grating, we see that the candle's light is diffracted into a full rainbow, but the remote control's light only shows a narrow dot. This proves that the infrared light is longer in wavelength than the red light because it's diffracted much further. I estimate that the wavelength is about 900 nanometers, which is very nearly the same wavelength as visible light. Not only can you see the infrared light with a camera, but you can hear it with a silicon solar cell connected to a set of computer speakers. You can also see it on an oscilloscope. It's kind of like Morse code. This is the number 1. Here's another trick you can try. Get a night light and dim the room so that it's barely turning on and off. Now with your TV remote control, you can make it flicker. You can reflect the signal from your remote control too. Point it at a white piece of paper and you can turn your TV on and off. But if you instead point it at a black piece of paper, it doesn't work. So what is the most important application of infrared light? Well, how about this one? Asteroids are very dark, almost invisible against the background of space, but they are relatively bright in the infrared. Using space-based telescopes that can see infrared light, we might be able to see the asteroids before they cross the Earth's path and cause extinction-level events. That might be useful.
Whether you love them or hate them, there's no denying microwave ovens are super convenient. They can heat food, like this, much more quickly than a conventional oven, although not always with the same results. But how do they, how do they work, right? Yeah, microwaves, sure, microwaves, great. But what the heck are those? That's a good question. Microwaves are a type of wave on the electromagnetic spectrum, and they're kind of sandwiched between radio waves and infrared radiation. In the case of microwave ovens, the most common wave frequency is roughly 2,450 megahertz. Waves in this frequency range have an interesting property. They're absorbed by water, fats, and sugars. And once they're absorbed, they're converted directly into atomic motion, heat. These waves have another convenient property though. They are not absorbed by most plastics, glass, or ceramics. Metal, however, does reflect microwaves, which is why it's a bad idea to leave a spoon in your cheese dip when the microwave oven's on. Not that any of us have done that. You'll often hear people say microwave ovens cook from the inside out, right? That's the key to the speed. Well, think about it like this. Let's say you're baking a cake in a conventional oven. Normally you'd bake this at 350 degrees Fahrenheit or so, but this time you accidentally set that bad boy for 600 degrees Fahrenheit. The outside of the cake is gonna burn before the inside even gets warm, and you will have ruined somebody's birthday. In a conventional oven, the heat has to migrate by conduction from the outside of the food toward the middle. Hot, dry air on the outside evaporates moisture, so the outside can be crispy and brown, like the crust on bread, while the inside is still moist. In microwave cooking though, the radio waves penetrate the food and excite the water and fat molecules more or less evenly throughout. No heat has to migrate toward the interior by conduction. There's heat everywhere, all at once, because the molecules are all excited together. There are limits though. Microwaves penetrate unevenly in thick pieces of food. That means they don't make it all the way to the middle, basically. And there are also hot spots caused by wave interference, but you get the idea. The heating process is different because you are exciting atoms rather than conducting heat. Inside a microwave oven, the air is at room temperature, so there's no way to form a crust. That's why microwavable pastries, or Hot Pockets, sometimes come with this little sleeve thing made out of foil and cardboard. The sleeve reacts to the microwave energy by becoming very hot. This exterior heat lets the crust become as crispy as it would in a conventional oven.